In question number 6, find the dimension of the specific heat capacity, the coefficient of linear expansion alpha, and the gas constant capital R, and the equations are given to us. So let us see in question number 6. First part is the dimension of specific heat capacity, and the formula is given as Q is equals to mc T2 minus T1. तो यहाँ पे मैं आपको बता देता हूँ जो Q है that is the heat energy, m is the mass, and this is the increase or decrease in temperature. Absorbed energy, absorbed or released, and this is increase or decrease in temperature. So we can say it has a dimension of energy, m has the dimension of mass, this quantity in the bracket has the dimension of temperature. So from here the dimension of specific heat capacity will be dimension of heat energy divided by dimension of mass divided by dimension of T2 minus T1. So it will be, energy is your m raised to power 1, L raised to power 2, T raised to power minus 2, and mass m raised to power 1, and temperature you can say Kelvin, so K is the symbol for that, K raised to power 1. So from here we can say your m cancel out with m, so we have L raised to power 2 and your T raised to power minus 2 and K raised to power minus 1. So this is the answer of part A. In part B we have to find the dimension of linear expansion, coefficient of linear expansion alpha, and the formula is given to us is length at some time t is equals to original length plus 1 plus alpha T2 minus T1. तो यहाँ पे मैं आपको बता देता हूँ. So this quantity is your length at say T2 when temperature was T2, and this is your length when at temperature T1, and this quantity is difference in temperature. So if we see, this one is dimensionless, so this product has to be dimensionless because ये यहाँ पर add हो रहा है, both should have the same dimension, so it must be dimensionless. तो यहाँ पर मैं लिख सकता हूँ dimension of alpha into dimension of T2 minus T1 must be equals to 1. So we can say your alpha has the dimension of like this T2 minus T1, and I can write this as K raised to power minus 1 because it has the dimension of K. So in the third part we have to find the gas constant dimension, and the formula is P equals to nRT. And formula is P equals to nRT. So here your P is pressure of the gas, ideal gas, and V is the volume of the gas, N is the number of moles of the gas, and T is the temperature of the gas, and this equation is called ideal gas equation. So from here the dimension of R will be dimension of P into dimension of V upon dimension of N upon dimension of T. So pressure is force upon area, so that will be m raised to power 1 L raised to power minus 1 T raised to power minus 2, and this is volume, so it has a dimension L raised to power 3, mole MOL, and your temperature, it has the dimension of K. So from here what we'll have, m raised to power 1 L raised to power 2 T raised to power minus 2 K raised to power minus 1 mole raised to power minus 1. So this is the dimension of gas constant. In question number 7, taking force, length and time to be functional quantities, find the dimension of density, pressure, momentum and energy. So in question number 7 we have given force, time and length as base quantities, and we have to find the dimension of density in terms of these base quantities. Okay, so we know that density is equals to mass times volume, and we also know that the force is equals to mass into acceleration. So from here if we substitute mass here, so what we'll have, density will be force upon acceleration into volume. So we can write force as the dimension of F raised to power 1 because it is the base quantity. Acceleration is L raised to power 1 T raised to power minus 2, and volume is L raised to power 3. So from here we can say it will be F raised to power 1 L raised to power minus 4 T raised to power 2. So this is the dimension of density. In B part we have to find the dimension of pressure, and we know that pressure is equals to force upon area. So it will be, so the dimension of pressure will be dimension of force divided by dimension of area. So it will be F raised to power 1 divided by L raised to power 2. So from here we can say F raised to power 1 L raised to power minus 2. So that is the answer. In the third part we have to find the dimension of momentum. Okay, by Newton's second law your rate of change of momentum is equals to force. So we can say the dimension of momentum will be equals to dimension of force multiplied with dimension of टाइम. ठीक है, इस टी को हमने वहाँ मल्टीप्लाई कर दिया टाइम को. So from here we will get F raised to power 1 T raised to power 1. So this is the answer of part C. And in the D part we have to find the dimension of energy. And the dimension of energy is same as the dimension of work done. So we can write work as force into displacement. So the dimension of energy will be dimension of force time dimension of displacement. So it will be F raised to power 1 into L raised to power 1. So it will be F raised to power 1 L raised to power 1. So this is the answer of part D. In question number 8, suppose the acceleration due to gravity at a place is 10 meter per second square. Find its value in centimeter per minute square. So we have given that your acceleration due to gravity is 10 meter per second square. So if you want to convert it into centimeter per minute square, so we can say your 1 meter is equals to 100 centimeter, and you can say 1 minute is equals to 60 seconds. So this thing we can write like this: G is equals to 10 times 1 meter, and this thing can be written as 1 second raised to power minus 2. So we can substitute 1 meter in terms of centimeter and 1 centimeter in terms of minutes. So it will be 10 into 100 centimeter into 1 second will be 1 by 60 minute raised to power minus 2. So from here what we can say, 10 into 100 into 1 by 60 raised to power minus 2 is into centimeter minute raised to power minus 2. So from here we can write this thing as 1000 into 60 square centimeter minute raised to power minus 2. So it will be 3600. So we can write 3.6 into 10 raised to power 6 centimeter minute raised to power minus 2. So this is the answer of question number 8. In question number 9, the average speed of a snail is 0.02 miles per hour and that of the leopard is 70 miles per hour. Convert these speeds in SI units. So speed of snail is 0.02 miles per hour, and we have to convert this into SI units. So we have to convert miles into meters and hours into seconds. So we know that 1 mile is equivalent to 1.6, approximately 1.61 kilometers, and 1 kilometer is equals to 10 raised to power 3 meters. So it will become 1610 meters. So 1 mile is equals to that many meters, and 1 hour is equals to 60 minutes, and 1 minute is equals to 60 seconds. So it will be 3600 seconds. So now we can substitute the value of 1 mile here. Then speed of snail in SI units will be 0.02 into 1 mile divided by 1 hour. So it can be written as 0.02 into 1610 meter upon 3600 second. So when we solve this thing, it comes out to be 8.9 into 10 raised to power minus 3 meter per second. And the second part is the speed of leopard. So speed of leopard is given as 70 miles per hour. Again we can write this thing as 70 into 1 mile upon 1 hour, and then we can substitute the values. 70 into 1610 meter upon 3600 seconds. So it comes out to be 31.3 meter per second. So this is the answer of question number 9. In question number 10, the height of a mercury column in a barometer in the Calcutta laboratory was recorded to be 75 centimeter. Calculate this pressure in SI and CGS units using the following data. So we have given the specific gravity of mercury is 13.6 and the density of water is 10⁻³ and the acceleration due to gravity is 9.8 meter per second square at Calcutta. Pressure is given by rho GH in usual symbol, where rho is the density, h is the height of the column, and g is your acceleration due to gravity. So in question number 10, h is given as 75 centimeter and specific gravity of mercury is given as 13.6. So if you want to find the density of mercury, you have to multiply specific gravity with the density of water. So density of mercury will be specific gravity into density of water. Okay, and g is given as 9.8 meter per second square. So if you have to find in SI units, so your pressure, that is rho GH, so in SI units it will be rho will be your 13.6 into 10⁻³ g is 9.8. ये तो ऑलरेडी हमारे SI यूनिट्स में है, तो इसको चेंज करना पड़ेगा. दैट विल बी योर 0.75 meter. So when we solve this thing, it comes out to be nearly 10 into 10⁻⁴ your Newton per meter square. So in CGS, pressure will be 10 into 10⁻⁴. This Newton, 1 Newton is equals to 10⁵ dynes, and 1 meter is equals to 10⁻² centimeters, so 10⁻² centimeter square. So from here what we'll get, 10⁹ minus 4 dyne per centimeter square, so it will be 10 into 10⁵ dyne per centimeter square. So this is the answer of question number 10. Okay, if you have any doubt in these questions, you can ask your queries in the comment section. Thank you.